Hello everyone, my name is Clarissa de Paula Dias and I will present my paper titled as Optical Characterization of Indoracyanide Interorganophosphatide Intermediate Band Solar Cells. And this work shows a study of samples with the intermediate bands were ground with indoracyanide quantum dots and their characterization regards optical properties by photoluminescence. My presentation was divided into a topic introduction, the theoretical fundamentals covered, what materials and methods are used, the results and conclusion. Well, we have observed that energy for fossil fuels is responsible for a large emission of dioxide carbon in the atmosphere. As a result, a range of environment problems has been aggravated due to increased consumption of this energy. And in this situation, new technologies have been studied seeking clean energy sources. One of them is a solar energy, and the solar energy is the focus of this work. So, interested in studying photovoltaic device has grown on among that then solar cells have been advancing in terms of quality and efficiency of a photovoltaic materials. Study of multi-junction, simple junction, and intermediate band solar cells were made. Multi-junction solar cells have shown an energy efficiency of 47.1%. However, according to a study by Luke and Martin, intermediate band solar cells found an theoretical efficiency of 63%. This result is compared to single function containing 41% and even multi-junction that containing 47.1%. Based on this concept, intermediate band solar cells have been proposed to increase efficiency compared to simple and multi-junction cells. They generate current while preserving the voltage of the device. This is a very observation. Yeah? And this happens because the energy level are inset in the gap of the material, forming the intermediate band between in the valence band and the conduction band. That figure shows exactly this. Absorbance of photon with energy behavior, then the gap, are also permitted excited electron from the valence to the intermediate band, represented by green arrow, associated to energy A8. Okay, and from the IB or intermediate band to conduction band, represented by red arrow, associated to energy EL. In addition, there is a common photon absorption of energy greater than the gap represented by blue arrow. Okay, the intermediate band is composed of quantum dots. What the quantum dots? Quantum dots, they are three-dimensional structure that arise during epitaxial growth from the difference in the latest parameters of the materials. This is a principal characterization of the quantum dots. They are able to confine the electron in three dimensions. This is the difference of the other solar cells. continue my study, I increase the material and methods. To perform the experiment mentioned, 4 samples were grown. The growth follows this sequence. One a substrate, a gallium arsenide perth layer was ground. Next, a thick indium gallium phosphide layer was deposited with the substrate, as shown in this scheme. Immediately after indium arsenide KDs were ground with different growth times, as shown in the table. The quantum dots were covered with a 4 nanometers gallium arsenide cap layer at the same temperature. It's represented by the cycles here. After that, a thick indium gallium phosphide layer is ground and the new KD growth cycles it repeats 4 more times. After 50 KD layer, no gallium arsenide cap layer was ground, leaving the last KD layer uncovered. And this can be used to take measure of the surface of materials. And then these are different growth, the times of dots, and the column shows the mean height of dots for each type. Okay, that's my results of my experiment. The optical properties of indium arsenide quantum dots have been investigated by photoluminescence, specifically to obtain information about the optical transition of KD structure. Okay. The following graph shows the PL spectrum for each sample at different temperature. I use the range from the 77 Kelvin to the 300 Kelvin. And this figure represents four samples with 4 different deposition times. So, by experiment, we find the first peak intensity at 1.30, 1 electron volts, and a second peak, one of high intensity at 1.36 electron volts. We define I1 and A1 the intensity and energy of the fundamental states, and I2 and E2 the intensity and energy of the excited states. This scheme here, this is the fundamental and excited electronic states in the KDs. These are related for PL measurements, especially. And this process was repeated for all samples. Sorry. And I repeat for the different times, and I will obtain more results for the comparison. Okay, continue my study. The graph below describes how the ratio I1 and I2 varies in function of the temperature. We observe that the 4 samples show a similar behavior exhibiting and increasing the I1 and I2 ratio up to a temperature is 230 Kelvin. We observe that while a higher temperature, this ratio we observe that starts to decrease. The behavior is still being investigated. More details of analysis of the experiment curve will show us with the decay when the temperature increases. I don't know yet. And continue my study, here, two graphs describe the behavior of the fundamental state, A1, and the excited state, A2, energy as a function of the temperature. We observed that a singular energy for the first time, 3 times, yeah, while the 3 seconds time, both energy A1 and A2 are higher. This means that KDs with higher deposition times coalesce, decreasing the optical quality. So this emission is associated with a layer or a internal layer that's formed during the capillary process. And this is a partial conclusion. I will study about more. Once done, let's continue. Terabyte, we performed simulations now using the Next Nano software. And the Next Nano software that solves Schrödinger equation for 3-dimensional semiconductor structure. And then we simulate different KD heights and diameters where the lowest KD is transition. Energy was fixed in 1.31 electron volts. This result is according experiment results, okay, for this sample 3. We introduce gallium in the quantum dots with gallium contents ranging from the 5% to 50%, as this graph shows this. And now, looking at these results here, what combination of highs and heights will give a 1.36 electron volts for excited states? The next graph shows this. Considering a 30% concentration. One moment. Okay, consider a 30% concentration of gallium. In KDs, according to the calculation, the KD must be 1.8 nanometers height and with a 30.6 nanometers diameter, and increase more increase 14% to KDs must be 2.12 nanometers height and 14.8 nanometers diameters. For concentration up 50% gallium, we reach 3 nanometers height and 60.4 nanometers diameter. As a result, we observe a gallium interfusion from the gallium arsenide cap layer to the indium arsenide KDs, forming indium gallium arsenide KDs with at least 30% gallium concentration for small dots that can reach 50% for dots with 3 nanometers height. There's a show this figure, and there's a show the blue line. This study is in the progress for the other samples in order to get comparison results. My goal is compare the results, experiment results for simulation results about all samples. Okay. That the conclusion is optical properties of indium arsenide, indium gallium phosphide KD structured by photoluminescence or different results and at different temperatures were studied and correlated with theoretical calculation. We observed two of the gallium interdiffusion from the gallium arsenide cap layer to indium arsenide KDs, at least 30% gallium concentration for small dots, and 50% concentration for dots with 3 nanometer heights. And the diffusion mechanisms in KD's growth is a very important in order to design new intermediate band solar cells with the ideal subband gap energy combination. This study still continues to obtain different results and different combination and hide and read about the quantum dots. And this is my references, and thank you very much.